and then it's going to react somewhere and turn back into an electron and go forwards in time. And what we see is this electron, anti-electron, electron, anti-electron pattern woven into the universe. So every electron we see, maybe it's the same particle. Now, does that seem plausible? What's the problem with that? And this is, I mean, everybody, we'll acknowledge this is the problem.
Faster than speed of light.
If we look into nature, how many anti-electrons are there compared with electrons? Yeah, there's virtually no antiparticles, right? So we live, either the universe is really skewed in the direction of particles compared with antiparticles, or we happen to live in a part of the universe that is just made out of particles, right? Maybe the next galaxy over is an anti-galaxy, right? It's made out of anti-electrons, that's where all the antiparticles are. There's a problem with that too. If there were really galaxies made of matter and galaxies made of antimatter, what would happen if they ran into each other? Yeah, you start to see all these reactions taking place. And we do see galaxies that are in the process of running into each other, and we don't see evidence of matter-antimatter reaction in colliding galaxies.
But it'd be like phenomenal amounts of energy.
Yeah, maybe they're, yeah, right. And we do see reactions that release phenomenal amounts of energy, but we haven't identified anything as a matter-antimatter reaction. So we'll see. Kind of an interesting idea that you could weave the universe out of, well, you need one quark, and you need one lepton, right? That's it. Make the whole universe out of that. Okay, so number of quarks. We have 0 on this side. How many quarks are on this side? I don't see anything resembling a quark, right? So did we conserve quarks? We sure did. What about number of leptons? How many leptons do we have on the left? We don't have any leptons on the left, right? Leptons would be what? These guys, here we go. Here are the leptons right here. Any of these guys on the left? No, any of them on the right? Yeah? How many net on the right?
0.
Well, there's a lepton and an anti-lepton, so no net lepton, so that works. What about charge? What about electromagnetic charge? How much electromagnetic charge do we start with on the left side? We started with +1. How much electric charge do we have on the right side? We have +1. Yeah, that checks out too. So anytime you go all the way through the list and you can check all the boxes off, that reaction happens, right? Those are the reactions that we actually see in nature, but can't check the boxes off. It says we don't ever see that reaction take place. Now, rules. So what will happen, what doesn't. All right, anything else that we want to talk about in that chapter? We'll take a look at some homework problems from 42. I just want to make sure that we've looked at everything we're going to look at in 43. Oh yeah, here's something else we need to talk about. Let's see.
So when are we finishing 44 then? It seems like we're going through in one chapter or lecture.
Well, what we did was we did 42, kind of like that.
And we did apparently 43.
Yeah, but we've got next Tuesday to come back. So on the schedule, we've got Tuesday to come back and look at examples from both chapters, 42 and 43. So we've got 2 days for elementary particles and 2 days set aside for astrophysics.
Oh, so there's going to be a little...
And there's a day of review at the end of all that too. Okay. So we will. We are moving a little faster right now. We want to get out ahead of the game. Try and stay caught up as best you can so that we'll have plenty of time. We'll have time for review. Okay. All right, let's see. I have a reaction like this. Let's say that reaction consists of what? I take 2 electrons, I fire them towards each other. They repel each other and they push away. So what this might look like in the lab is I get an electron beam here, and I get an electron beam here, and I fire them at each other, and they repel, and I see an electron go this way, and I see an electron go this way. And I just want to know how to draw the diagrams on this So I guess the question is, if I start with an electron here, and I have an electron here, is this what happened? Is this electron, let me see, is this electron coming out the electron that went in here? If this is electron A, and this is electron B, and I'm going to call this electron C, and this is electron B, is the identity of electron C the same as the identity of electron A? Can I follow the electron through the reaction and keep track of where it is? And in general, we can't. So what we have to do is say, this is one possibility of something that happened. This would be mediated by either a photon or a Z particle. And then the other possibility is that this electron went in, this one went in, and this one actually came out here, and this one came out in this direction.
That was a silly question. There's no
Yeah.
anti-electrons anywhere, right? Those are
No, there's no
just-
anti-electrons in this example.
Those are just negative.
Yeah, this one there's no anti-electron. So which was it that took place? And again, I could have a photon or a Z particle here. And quantum physics says they both happen, right? You guys remember the two slit experiments with photons? Which slit did the photons go through? They kind of went through both. What I had to do was consider the photon went through the left slit and it went through the right slit. And how did we do the calculations on that? What we did was we said that there are two possible paths, path 1 and path 2. And then we had to come up with an amplitude for each one of the paths, amplitude 1, amplitude 2. And we had to come up with a relative phase. And how did we finally come up with the intensities? And what we would do, yeah, we got an A total by looking at the A1s plus the A2s. We took all the amplitudes, we combined them together, including phase effects, right? And then how do we get the intensities? A total squared. Okay, so that was when we had 2 slits or 3 slits or whatever. We would add together all the amplitudes and add together all the phase effects. How is that the same as this example right here? Each diagram has an amplitude. So for each diagram that we come up with, there's a set of mathematical calculations we do, and each diagram has what is analogous to an amplitude for the individual diagram. So we'd say this diagram has amplitude 1, this diagram has amplitude 2. We would have to allow for phase differences between them, but we would use those, come up with an A total, and then square that for the overall intensity. And intensity here is saying, what's the likelihood of this happening? Okay, and to get the numbers right, we actually have to do this. I mean, to make the correct predictions, when we use quantum rules of taking this, combining this, introducing interference effects, so there's interference taking place between these two diagrams. And then squaring the overall A total, it just works perfectly. It makes just exactly the right predictions. We go, we build the machines, we build the electron beams, we fire them at each other, we look at the energies and the angles, and it just matches exactly what we would predict. But built into this is this crazy idea that whatever paths could have taken place did take place. And what that leads to is the idea is, I can't say that this is the same electron that left here. Okay, it's some combination of this electron and this one, but I had to include both possibilities into the calculations. Okay, and since we keep getting the right answers as far as what matches what we see in the lab, we think we're on the right track. But it says that if we're not paying attention, all the electrons in nature could get up and switch places, right? When we're looking the other way, electrons say, let's get up and trade places, see if they can tell. And we get up, we turn around and go, no, looks the same. I didn't see anything happen. And quantum physics allows for that possibility, right? All the electrons get up and switch chairs when we're not paying attention, or when we're paying attention. That's one of the things that's just ongoing all the time. So it leads to this idea, this is weird. I want to write this down because it attaches a word to this. This effect is called indistinguishability. And the idea is if I do this with a pair of electrons, I can't tell because every electron is just like every other electron. What if we change the reaction? What if we change just the E muon goes the E muon? We'll have a much better idea, right? The muon that went in, actually I can't guarantee it here either. There's other reactions that could turn things around for us. But the muon that went in is somehow related to this muon that came out in a more direct way. Here it's kind of 50-50. I can't tell which happened. Okay. That's it. All right, any questions on chapter 2? On chapter 42, sorry, I left the further up. Yeah, any questions on chapter 2, actually?
That's like dimensional analysis, right?
No, that was one-dimensional motion. So if we have a car going 20 meters per second, and it slows at a rate of 5 meters per second squared, how far will it travel to a stop? All right, let's look at some examples from 42. 42 was what? That was the nuclear fission, nuclear fusion, radiation exposure kind of chapter. Well, I have a couple of problems I want to look at, so I'm going to do that. I kind of was interested in 27, in chapter 42. '27 said that all right, here's a house. Here's a door, here's a window. And what we're going to do is we're going to build a little fission reactor on the side of the house. We're going to go off-grid, right? We're going to cut electrical cables and say, hey, I'm going to just generate my own electricity. And I'm going to build this little fission reactor out the side of my house. How much uranium do I need to order for the year? Assuming the government will let me do this. How much uranium will I need for my annual electricity usage? And what this suggests is, it says a typical house operates at about 880 watts, averaged over day and night. So that gives me a power average. And I checked my PG&E bill and it's pretty close, actually, to my electrical usage. So at nighttime, everything's turned off, right? But in the daytime, this is getting used at maybe twice or 3 times the rate. And if you average over the whole day, it's like 880 watts. So that's like 880 joules per second. That's the rate of electrical energy usage. How much energy is that going to be for the whole year? You go, well, 1 year, right? 1 year is equal to, what did we decide it was? 31.6 million seconds? Something like that. And then we're using energy at what rate? 880 joules per second. So I ended up with the energy for the entire year, 2.78 10 to the 10th joules. All right, that's my electrical energy usage for the entire year. How much uranium do I need to come up with that much energy if I plan on fissioning all the uranium? So I can start with that number. 2.78 10 to the 10th joules. The first step here is I want to go from joules back into MeV. Okay, we did some similar problems like this last Thursday, I guess, kind of in the other direction, I think. This time I want to switch and go from joules back into MeV. So let me do that, 1.60, 10 to the minus 13 joules. Now the MeV is going to let me figure out how many uranium nuclei I need. And remember, the book uses this estimate. They say that each reaction with uranium-235 is supposed to give us about 200 MeV. So we get to use that until they tell me something different. I'm going to keep using that number. In fact, it's probably built into the problem. Yeah, it says that at the end of almost all these problems. Assume 200, assume 200. So that's not a minus sign, that's an approximation. I'm going to just erase that. So now I know how many uranium-235s I need, right? How much mass will that be? How do I get from number back into mass? Yeah, so let's use a molar mass number. So if uranium-235, that's going to be 235 grams of uranium-235 for every mole. So this is 1 mole of uraniums, and each mole of uraniums is going to have a mass of 235 grams, right? All right, so I think we're set. I think we got everything calculated. Yeah. So what did we do? We calculated joules. We canceled the joules out here. We canceled the MeV here. We canceled numbers of uranium here, and the units are coming out in grams. Okay, so this is all my electrical needs for the whole year, right? I'm going to run my dishwasher and my washer and my dryer and everything, all the lighting, all the appliances. And I need 0.340 grams of uranium-235 to do that.
How much does that cost?
I don't know. What's the cost of uranium?
Yeah, it's a whole year of power.
It's going to be pretty high. But so that's assuming 100% efficiency.
That's assuming 100%
so
efficiency.
Generally be like 97, 98.
Sure. Well, let's decide. I had to build a fission reactor. How much is it going to cost?
Millions.
That's not critical mass. This will not work. There's a certain size of uranium that I have to start with. Why? So one step to the next, I've got to sustain the neutrons. So the neutrons have to set off an additional reaction, and that's going to require a certain minimum amount of uranium-235, so I don't get to go off the grid. Instead, what we're going to do is, instead of everybody building their own fission reactor on the side of their house, I guess we build a nuclear power plant, right? We build a big nuclear power plant, and everybody's using 0.34 grams, or a full gram, maybe, an entire gram, of uranium to meet their electrical needs for the year. Okay, yeah.
Can fission be done with other things like americium?
No, not, I don't know. Americium,
Because
I
I
don't
just
know.
like that's in smoke detector, so you can't actually get like lots.
Oh, that's right. So we could run it off of the smoke detector.
Yeah.
Not fission. So there's a radioactive process that goes on in the americium and in the smoke detector, but it's not fission. It's not going to give nearly as much energy.
I think you can fission.
You can
all of those,
americium.
though. Yeah.
Okay. So
But it's not something we're interested
yeah.
in.
So you have
Well,
to spend so much energy to
Yeah.
create it in the
That's
first
the
place,
problem.
and it's completely.
There's
yeah,
not
how do
even
we generate all of it? So what we do have is an isotope of thorium in it. There's some isotope of thorium that fissions pretty reliably, and there's a fair amount of thorium around. There's uranium-235, and then the other one that we've made in large bulk is plutonium-239. But this was possible because why?
We bombed.
It came from uranium-238, and it was not much of a step. Americium is farther. You've got to run a series of steps to generate americium. I don't know how expensive it would be. I mean, it's in smoke detectors.
It's like a really small amount.
How,
Detectors.
yeah, right. How expensive could it be? I don't know.
You can get it.
You can. So, if any of you guys are interested, there's a story here that, where did I find this? A student brought it. It's called the Radioactive Boy Scout. There was this kid in Minnesota, Michigan, something like that. He got really interested in nuclear fission, decided to build his own fission plant. So he found out where uranium ores were. He bought a Geiger counter, borrowed the family station wagon, and went out with his Geiger counter and found uranium, found radioactive sites, and collected the rocks and brought them back. And found out how to run chemical reactions and sort out the uranium, enrich the uranium. And then he had read that if you take an alpha particle and run it into aluminum, the aluminum absorbs the alpha and creates a neutron. So there's his neutron source. And he didn't get a sustained fission reaction, but he did build something that was generating, he was running fission. I mean, there was fission going on.
In his house.
Yeah, well, in his mom's garden shed that he'd taken over. And eventually, the feds got concerned because this kid was sending, this was like 20 years ago, he was sending letters around to all the national labs asking how he could get samples of radioactive material. And at some point they got a little nervous, and they went in, and they found that he had he was running fission in his backyard in his mom's shed. Yeah, so.
Uranium costs yellow pig U308 is $36.25 per pound currently.
Is how much?
$36.25.